Okay, this is 6.1 homework help. All right, the first problem wants us to sketch this vector in the plane. So 3i, 5j means just it goes over 3 and up 1, 2, 3, 4, 5. So the vector, if I place the tail at the origin, would go over 3, up 5. Now, the thing about vectors is it doesn't matter where you place them. I could move it up, place it here, can move it over, place it here. The key is that it has the same length, because that represents the magnitude, and it has the same direction, and that would be the angle with horizontal, which would be the same for all these vectors. I could even place it here, as long as it's got the same angle with horizontal and the same general direction. Now, another thing about vectors is I is this unit vector that goes right here. So that would be the unit vector over 1, up 0, and j is the unit vector that goes up right here. So that would be the unit vector over 0, up 1. And you can see how this applies if you start writing this out, because 3 times the unit vector 1, 0 plus 5 times the unit vector j, 1, 0. And when you multiply, you get 3, 0 plus 5, 0, which is just the unit vector 8, is the unit vector 3, 5. So you can see how, there's different ways to represent it. You can represent it like this, or you can represent it like this, but that's what that I and j is all about. Now, if I select all that apply here, I would select that it has a length of square root of 34, and that they all point in the same direction. All the other ones don't apply. You can read through them, but if you do the Pythagorean theorem on this triangle right here, this is 3, this is 5, and you do get the square root of 34 then for the hypotenuse, which is the length, and everything else doesn't apply. Okay, the next problem wants us to find a vector A that goes from negative 4, 4, which is back here, all the way up to 2, 7, over 2, up right here. So the vector goes like this, and we know then we can count. It goes over 6, up 11. Or we can subtract. The other thing is you can subtract the y-coordinates. You have 7 minus negative 4, which gives you the y-coordinate of 11. And then you also have 2 minus negative 4, which gives you the x-coordinate, which is 6. So there's our vector that goes over 6, up 11. And don't forget to use these pointy brackets here for our component form of vectors. Okay, this next problem is going to have us set up a system of equations, because it says that some number s times vector A, so let me write that. Vector A is the vector 3, 5, plus some number t times the vector b, which is 3, negative 5, has to equal the vector 3, negative 15. So if we just distribute the s here, we get 3s plus, I'm going to take the x-coordinates of both these vectors, which would be 3s plus 3t, and set it equal to the x-coordinate of this, which would be 3. And then I'll do the other one, so I'll do the y-coordinate. S times 5 is 5s, plus t times negative 5 is negative 5t, and that has to equal the y-coordinate, negative 15. So there's my system of two equations with two variables. Now I can solve this system. I'd probably solve it by dividing through by 3 in this first equation. So I get this, and then I'd subtract t from both sides. And then I can substitute Sn. That seems like a pretty easy way to do it. Now if we substitute 1 minus t in, we get this equation. And if we finish it off with algebra, we get t equals 2, and if you plug t back in right here, you get s equals negative 1. We can go ahead. Those are our components for our vector. This next one's pretty straightforward. It wants you to resolve these vectors. I is just, the vector 1, 0, and j is the vector 0, 1. So it's not hard to then see a is over 2, up 1, so it'd be 2i and 1j. B is then negative 2, up 1. V is over 2, down 1. And W is back 2, down 1. Okay, the next problem says we have a truck that's headed due north at 70 kilometers per hour. And we also have a police car that's headed west at 75 kilometers per hour. And in 1 hour, now we have a distance. If we multiply by 1 hour, that's just 75 kilometers. And then the same thing here. If we multiply by 1 hour, we just get 70 kilometers. So the question says, find the velocity currently representing the displacement. So we're looking for a displacement vector of the truck with respect to the car. So that would be this vector here of the truck with respect to the car. That's negative 75, comma, negative 70. The next problem wants to find a vector v in 2 dimensions with a length 7 pointing up at an angle of 5 pi over 6 from the positive x-axis. So let's draw that real quick. We know 5 pi, if this is the positive x-axis here, so if you rotate around 5 pi over 6, we know that's on our unit circle right here, 30 degrees from 180. So we're looking for this vector right here, which we need the x and y components here and here. We know normally this is negative square root of 3 over 2, and this is 1/2 if the hypotenuse is 1. But now being that it's 7, we have to multiply these by 7 so that our Pythagorean theorem works. So we're basically just, the unit circle, you can look at it as here, and these are, you know, with a hypotenuse of 1. So we have to make these 7 times longer, each of the sides. So we're basically making a similar triangle that's bigger. So there's our answers here. Negative 7 square root of 3 over 2 and positive 1/2. I'm sorry, 7/2. And we're not going to worry about 3-dimensional vectors for now. You're going to learn later that you can draw, you know, an x, a y, and a z axis. And you can do these vectors in 3-dimensional space then. And you'll do that later in math, but we're going to hold off on that for now. All right, the next problem says we have vector v, 2-dimensional, and it's got a magnitude of 13. And then it also says it has an x component or I component of 5i. So what that means is the vector goes over to the right, 5. And somehow it's got a hypotenuse of 13. So it's either this vector here or it's this vector here. Now if we do the Pythagorean theorem on these right triangles, we find that this leg is 12. So this would be negative 12. So our two answers for the vectors are 5, 12, and also 5, negative 12. Next problem gives us two vectors u and v, and just says do some operations with them. So when you add vectors, you just add the x components and you add the y components. That's pretty straightforward. When you subtract them, same thing, 2 minus 1 gives you 1. Just subtract them, and negative 5 minus 3 gives you negative 8. This time other way around, we have v minus u, so it would be 1 minus 2, which is negative 1. And then we have 3 minus negative 5, which would be positive 8. And then we have 4 times vector u, so you just distribute basically, and you have 8, negative 20. And then you have 1/6 times v, so that, I'll write that right here. Negative 1/6 times v would be negative 1/6, comma. And then we have negative 1/6 times 3, which gives you negative 1/2 if you simplify. And then last we have 4 times vector u. I'm just going to write this out so I can show you the work a little more clearly. There it's written out where I substituted u and v in. And now I just basically distribute. Now I distributed the negative 8, so I distribute the negative 8 to both of these. You could have left the minus sign there and distributed the positive 8 and then subtracted the vectors. Either way. But when you do this, you end up getting 0 and then negative 44. And that goes right there. All right, the next problem gives us two vectors, u and v, and they say they're sides of a parallelogram, and we want to find the lengths of the diagonals of this parallelogram. So for simplicity's sake, I'm going to place these at the origin. So I'm going to go back for vector u. And for vector v, I'm going to go over 1, 2, 3, 4, and down 4. So that way, we've got two sides of the parallelogram. Obviously, I can place the other vector u right here, where it goes over to the left, and the other vector v right here, and I've got my parallelogram. Now what I want is the diagonals. So I want this length here and this other length here. I'll do one at a time, and probably the law of cosines would probably be the easiest here. Actually, no, I'd say using graph paper would be the easiest because you got a right triangle right here. So there's 2 and 4, so you can just do the Pythagorean theorem with 2 and 4. That gives me the square root of 20. Then for this diagonal, and then this other diagonal here, I'm going to have to make a triangle here. The sides of this are 4 and 6. So the square root of 52 would be the length of the other diagonal. Next question wants a vector in the opposite direction of this vector u, so I think a picture always helps. This one goes back 3. We want a vector that goes in the opposite direction, half its length, so obviously we would do 3/2 forward. So this vector would have 3/2 comma 0 right here. And once again, we're going to wait on the three-dimensional vectors, but we will find vectors of a certain length in the same direction in this same homework assignment. We'll just stick to 2 dimensions though. You might like this problem. This one's pretty easy. Just add the x's and add the y's to add vectors together. Okay, then the next problem then says r is the point -3, 2, which is right here. And we want to find a point P such that the vector from P to R has components 2, 3. So somehow we need to go over 2, down 3 to get to this. So we're looking at this point right here. As you can tell, we need to go over 2, down 3. So you could basically just do the opposite, go back 2, up 3 to get to this point that we need for P. So that my vector PR is right here, over 2, down 3. So that point looks like it's -1, 2, 3, 4, 5, up 1, -5, 1. Okay, the next problem is pretty straightforward. It gives you a point P, which is -3, 4, so you go over 3, up 4, there's P. And then it gives you Q, which is 0, 9, here's 8, 9 would be one more up. So there's Q. We want to go from P to Q as our vector right there. So we can give that in order pair, over 3, up 1, 2, 3, 4, 5. So over 3, up 5 is our vector. Okay, the next problem wants to know if vector AB and vector PQ are parallel, and if so, do they point in the same direction? So I'm going to graph both these points real quick. We'll just give both these points, or all 4 of these points graphed. From A to B is this little blue vector here, a little hard to see, and then P to Q is this vector here. They do go in the same direction, and they are parallel. And you can tell because they go on a diagonal of up 1 over 1, a slope of up 1 over 1, which is like at a 45-degree angle. Because these are both isosceles right triangles. A little hard to see the small one, but that is a 45-degree angle. Hope that helps. Okay, when you're multiplying a scalar times a vector, it's really easy. You just distribute like we've already done. Next problem is similar to the problem we just did a second ago, only this time they want to know if they're equivalent. So we're going to graph all 4 of these points real quick and connect them. And if you graph the points, connect A to B and P to Q, you find they both go over 4, down 1. So yes, they are equivalent. All right, next problem wants the terminal point of vector A when it's based at the point 5, 4. So I'm going to graph the point 5. And then our vector A goes over 3, up 2. So there's our vector A right there. I usually put the little arrow over it. I know the books or the Webwork does just a bold letter, which is fine. But the terminal point then is this point way up here, which obviously we could add these two and get the point 8, 6. All right, the last problem we just want to add these together. So we have 5/2 plus 3, comma, and then we have 8/3 plus 4/3. So we need a common denominator over here, multiply top and bottom by 2. That gives us 6/2. And we can add these and get 11/2 for the x coordinate, x component. And the y component then would be 12/3, which is just 4. So there's our vector that we get when we add these together. All right, I hope this helps.